You wake up one night and look up at the stars. They seem fixed, permanent, safe. But somewhere out there, physics allows for an object so strange that nothing is supposed to ever fall into it. Only out. Tonight, you are going to fall into one anyway. It is called a white hole, and it might be the strangest object mathematics has ever predicted. You already know about black holes. Light goes in, nothing comes out. Gravity wins. A white hole is the mirror image of that nightmare. Matter and light can only come out. Nothing can go in, ever. Not you, not a photon, not a single atom. So what happens if you try anyway? To understand this, you have to go back to 1916. Karl Schwarzschild was serving on the German front during World War I when he solved Albert Einstein's field equations for the first time. His solution described a black hole, but buried inside the mathematics was a second, hidden solution, a time-reversed version of the same object, something that expelled matter instead of consuming it. Schwarzschild didn't live to explore it. He died months later from a rare illness. But the equation stayed, waiting. Picture it now. You approach the white hole in a small ship. From a distance, it looks almost identical to a black hole, a dark event horizon, a faint ring of light bending around it from gravitational lensing. But as you get closer, your instruments start reading something impossible. Matter is streaming outward from the horizon. Gas, radiation, possibly whole streams of exotic particles. All of it moving away from the center at incredible speed, like a cosmic fountain that never runs dry and never refills. You cut your engines and drift closer, curious. Can you enter? The answer, according to general relativity, is no. Not because of some cosmic doorman, because of causality itself. Time only moves forward for you, and for a white hole, the future is defined as being on the outside. Every possible path through spacetime near that horizon points away from it, not toward it. You could fire your engines at full power, aimed directly at the horizon, and you would still find yourself moving away. The horizon doesn't repel you. It simply removes the option of toward from the universe's grammar. Stephen Hawking once said that black holes are where God divided by zero. White holes might be where the universe refuses to let you divide at all. Now, here's the twist that keeps physicists awake. A black hole and a white hole may be the same object, seen from two different sides of time. In 1935, Einstein and physicist Nathan Rosen described a mathematical bridge connecting a black hole's interior to a separate region of spacetime. Today, we call it an Einstein-Rosen bridge, or, more commonly, a wormhole. In some versions of the mathematics, that far side isn't a different location. It's a white hole. Matter falls into a black hole here. It never reaches a floor because there is no floor. Instead, in principle, it re-emerges somewhere else, spat out of a white hole, into a universe that may not even be this one. You feel the ship's hull hum faintly, not danger, just the quiet math of general relativity, doing what it always does, refusing to be kind to your intuition. So, could a white hole actually exist, or is it only a trick of algebra? This is where things get complicated. In pure Einsteinian relativity, white holes are mathematically valid solutions. But there's a devastating problem. They violate the second law of thermodynamics. Entropy, the universe's tendency toward disorder, only increases. A black hole's entropy grows every time it swallows something. A white hole would require entropy to spontaneously decrease as it ejects matter in a perfectly ordered stream. Nothing we have ever observed behaves that way. Not once. Not anywhere. Roger Penrose, working through the mathematics of gravitational collapse in the 1960s, showed that any realistic collapsing star forms an event horizon that only lets things fall in, never out. In other words, nature seems to build black holes easily. It has never once shown us how to build the reverse. So most physicists now think of white holes the way you might think of a perfectly reversed video of a shattering glass. The physics of pieces flying together into a whole glass isn't technically forbidden by Newton's laws. It's just staggeringly improbable, because it would require every fragment's motion to be timed with impossible precision. A white hole is the shattering glass running backward. The mathematics allows it. The universe, so far, has never shown us the tape, and yet the story doesn't end there. In the 1980s, some theorists, including work built on ideas from physicist Igor Novikov, proposed that white holes might not stay stable even if they somehow formed. The moment even a single photon tried to fall toward one from outside, the resulting instability could collapse the white hole into an ordinary black hole almost instantly. In this view, a white hole is less like a locked door and more like a soap bubble. It exists in theory. It cannot survive contact with the rest of the universe. You imagine it now. A perfect white hole, spraying matter into the void, untouched, alone. For it to remain white, it must never encounter a single particle from the outside universe. The instant it does, it stops being a white hole and becomes the very thing it was defined against. There's one more possibility, stranger than the rest. Some cosmologists have speculated that the Big Bang itself might have been a kind of white hole. All the matter and energy of the observable universe, spilling outward from a single point 13.8 billion years ago, never falling back in, only ever expanding outward. Carl Sagan once said that we are made of star stuff, but perhaps we are also made of white hole stuff. The final cosmic scale eruption of everything that would ever exist, still expanding into darkness to this day. If that's true, then you have already fallen into a white hole. You did it the moment you were born into a universe already flying outward from its own origin. You are not approaching the white hole. You are the debris still traveling away from it. So back to your ship, hovering just outside that shimmering, matter-spraying horizon. You cannot enter. No one can. Not because of distance or fuel or shielding. Because the universe itself has decided, at the level of causality, that this direction does not exist for you. It is the one place in the cosmos where the answer to "what if" is not "you would die instantly," the way it is with a black hole. It is simply, permanently, you cannot. Maybe that's the real lesson hiding in the mathematics. Not every door in the universe opens both ways. Some structures exist purely to remind you that time has a direction, and that direction is not negotiable, no matter how fast your engines burn or how close you get. You pull away from the horizon and watch the faint stream of ejected light fade behind you. Somewhere, a version of you in the mathematics is still expanding outward from a point 13.8 billion years old, and always will be. You look up at the stars again. They still seem fixed, permanent, safe. But now you know that permanence was never really the truth. You are the ejected matter of an old, patient explosion. Still moving, still falling outward, and you always will be.